But it's my pleasure to introduce today's speaker, Michael Fu. Is one of our esteemed faculty member in the Institute. Michael received his master's and PhD degrees in applied mathematics from Harvard in '86 and '89. He also received his SP and SM degrees in electrical engineering and SP degrees in mathematics from MIT in 1985. So many degrees from Massachusetts. Since 1989, he has been at the University of Maryland in the Robert H. Smith School of Business. Michael is a recipient of many prestigious awards. He's a IEEE Fellow and also a Fellow of Institute for Operations Research and Management Sciences. Today, Michael is going to go over some of his exciting work that he's doing. I believe some of them in collaboration with Steve Marcus. So with no further ado, Michael.
Okay, thank you, Reza. Actually, not 80% of this work is not mine. It's an overview of simulation optimization. Maybe 90% even. I'll just talk, maybe the last part will be more of my research, but I'm just going to try to give a broad view of this field. And I didn't realize that the faculty that were going to be here, there's so many OR faculty, so I'd assumed that there would there would be people that wouldn't even know necessarily what OR is, so I apologize to Dave and Mike and Andre if some parts of this will be kind of boring to you, but I'm trying to reach the broad student audience here, so we'll see how it goes. So here's the agenda. I'll start with some acknowledgments, just ISR acknowledgement. Then I'll begin with advertisements, and this was actually supposed to be aimed again at students and people not familiar in the field, so there's some shameless advertisement for some of the books that I've done recently, but that's also for the OR field, the operations research field. Then I'll go into the main topic is what is simulation optimization, what do I mean? Because even though in OR we're pretty clear what we're talking about, there are other fields in engineering that may think of this as something a little bit different. So I'll clearly define what we mean by simulation optimization. Then I'll give some examples, talking about general examples, a few specific examples, some academic examples, and then some real-world examples as well, including some success stories, again, that were not my work, but other people's work, but I can tell you about it. And some of the techniques they used were actually, some of the methodologies were things that we developed, but they used it for real problems. Then I'll kind of give a very brief overview of a lot of the different methodologies in this field that are used. And you'll see this is kind of going through the table of contents in the book that I'll be going through, I'll be advertising in a second. And I'll focus on what I call two extreme points. So these are two specific methodologies. One of them is called statistical ranking and selection. And I'll focus on one little area of this very broad field. I mean, statisticians, there's hundreds and hundreds of papers on this field, but in simulation, there's certain community that's focused on this in the simulation field, and I'll talk about some methods that have been developed there. And then I'll talk about a little bit about stochastic gradient estimation, which is the field I've done most of my work in, but that's, as I said, maybe not more than 10% of the talk. And I call these the two extreme points because ranking and selection in terms of optimization is you're given a set of discrete alternatives, maybe 10 alternatives or 100 alternatives, and you're trying to decide which one's best. And the problem there is that each of your estimates of each of the alternatives is noisy. So then you have to decide, if you're doing simulation, which one of these alternatives to simulate given a certain budget or a certain level of probability that you're getting the correct one, and how you do this allocation is the main problem here. Whereas in the stochastic gradient estimation setting, what you're trying to do is you're looking at a continuous variable, so it's usually uncountable, some uncountable set. If it's one dimension, it could just be on the real line, and you're using basically gradient search. So here, you're not given a fixed set, it's continuous, you have to do a search through the search space. So that's why I call these the two extreme points in terms of methodologies. One is there's no search, basically it's all the statistical part, you have to figure out how to deal with the noise. The other one, there's also noise, it's a continuous variable problem. And then if I have time, and depending on how it goes, I'll talk about more recent research in mostly in that second area. Okay, so my acknowledgments, as I said, this is just over the years, people that I've worked with. Actually, I guess I omitted Mike from here, but sorry. I don't consider him a collaborator from ISR since he's in my department, but these are just, so NSF, AFOSR, semiconductor research, and had many students over the years, and the last two are applied math students who are being funded through ISR, and so some of the recent research I'll talk about is from their dissertation work. That'll be near the end, as I said, though. Okay, so here's the shameless advertisement. This book was just published. Oh, actually, I was going to show you a copy. It just published November 14th. That's why I requested the last. No, actually, I didn't know when it would actually come out, but here's a copy of the book. And it just came out in November.
Don't change this.
No, yeah, because I need to put this online.
Okay. I said the book is better than the movie, than this talk. So if you don't like what I talk about, you go get the book and read that. Okay. And for some reason, it has a 2015 copyright, even though it's already come out. Okay. And what's actually kind of ironic about this is that, this doesn't show up over there. Not sure why. Oh, okay. So this morning I actually got this email. It says, the date is this morning, December 3rd, Springer Alert subscriber, and here it is. The book is actually there. And, but then there's another one actually. So if you're, this just to show how popular is this other book by Abhijit Ghasavi, Simulation-Based Optimization. This came out the day before this, this is a little older, November 5th. So this came out last month. But he also wrote a chapter in my handbook as well. So that's kind of gives you an idea that this field, we've got a lot of people working in this area. So just to give you an idea that I go through quickly the table of contents, and it's partially color-coded here. These are all the chapters in the book. And so the last chapter is on Markov decision processes, which I won't be covering, which is similar to the work that I've done with Steve Marcus, but I won't be talking about that. The top parts I will be talking about is what I mentioned, ranking and selection and stochastic gradient estimation. And then in the blue are two areas that actually I'm using, the recent research is using stochastic gradient estimation in kind of novel ways in these two areas. So I'll be concentrating on the red, but then at the end I'll be talking how this number, the stochastic gradient estimation actually relates to some new methods in 4 and 6 and 7. These are some other books related in the area. This is back in 1997. This is the work that Steve Marcus and I did with one of our ISR PhD students who's now a faculty member at Stony Brook in the Applied Math Department, and a postdoc that we co-advised who's now at Sogang University in Korea. So that's more the simulation-based algorithms from Markov decision processes, but I won't be talking about that at all today. I will be talking about some of this stuff here in the 1997 book. I put this other book up here, which I just wrote one chapter to, but for the students, if you're interested in more about the general area of this field, there's these handbooks in OR management science, and volume 13 is on simulation. It was in 2006, and there's several chapters that treat a lot of these techniques in there as well. I think Mike was editor for several of these volumes too, right? Yeah. Okay, and the last promotion here for books is the Encyclopedia of ORMS, which was published last year, the 3rd edition. So again, if you want to find out more about different areas in OR, not just simulation optimization, but just other types of optimization, this encyclopedia is a good source. Okay, so last thing on this is, again, Informs, everyone knows IEEE, so in our field, Informs is, as Reza mentioned, is the main society. We have an annual conference, which we had 5,700 attendees just last month. And then the other thing related to this specific topic, the Winter Simulation Conference, that's the conference I go to every year, and they have a track now in simulation optimization. And the conference this year is actually next week, and I'll be giving a tutorial and having a panel actually on this topic, simulation optimization. But for students, the main thing I wanted to get across is the proceedings for this conference are freely available online. So if you go to this website, which hopefully I have here, right there, all the proceedings all the way back to 1968 are available online. Okay, so if you're interested in any type of simulation research, well, not any type, I'll have to define what simulation I'm talking about in a second. Once I define that, you can look here and you can find lots of different work over the last 30, well, actually that's all, how many years? 46 years there. Okay. So that's one advertisement for that. And some more freebies for students. Now, I don't know if you know this, if on Google you can get you can do spreadsheets and you can get Solver and Risk Solver, which does simulation online for free. So you can just go, let's see, I think I did it here. So you go to your Google, you go to Create, you go to Spreadsheet. Hopefully this works. You go to add-ons, you go get add-ons, and you'll look here, there's tons of add-ons here, but particularly for OR people down here, there's Solver, which does all the optimization. It's not as good as some of the stuff Andre works with, of course, but it's good for mere mortals. And then there's, down here, there's Risk Solver. I don't know where it went now, but on here maybe I already added it at some point. There's something called Risk Solver as well. Oh, there it is, right there. Okay, which allows you to do this Monte Carlo simulation that I'll be talking about. Okay. So, what kind of simulation am I talking about today? I'm talking about stochastic or Monte Carlo simulation. So, it's basically not just a differential equations type simulation. So that's a big distinction. It's stochastic, and it's usually discrete event systems. Okay, so it's not continuous time like in what you're used to when you solve differential equations. And the only exception is that we do in finance, we do stochastic differential equations. Okay, so but it's stochastic still. Okay, so the main thing is that these are systems with randomness in it. Okay, so which is why ranking and selection is kind of the most basic technique we use. So examples of these are queuing systems, production inventory systems, which can be applied to model manufacturing systems, supply chain networks, computer communication networks, transportation systems. So what do we mean by simulation optimization? Simply put, it's optimizing those systems that we just talked about that we simulated, right? But it's not completely consistent even in our own literature, because there's one ambiguity is where does the simulation come in? The way I described it in the last slide is the simulation is to simulate the system, so it's in the evaluation or estimating the performance of that system. But people also use the simulation optimization in terms of the search and randomizing. And if you're looking for a solution, they may use some what they call simulation to try to sample the solution space. So sometimes they use it for that. And in this talk will generally mean number 2, but even in that table of contents chapters I put down there where there's several chapters on random search, and there was also discrete optimization via simulation, they use number 1. They use randomization in their actual search as well. So most of the time it's number 2 here, but it can also mean number 1. And then people can also ask, well, what's the difference between simulation optimization and stochastic optimization? I would say that simulation optimization is a subfield of stochastic optimization, and many of the methodologies that were listed in that table of contents, people that say they do stochastic optimization, like stochastic approximation, would also use. But a lot of the work that I'll talk about exploits the fact that we're actually doing a simulation. So for example, if you're more general, could be things like physical systems that you can't simulate. So in ranking and selection, a lot of that work came out of things like drug testing or agricultural yields where they would use real data. Okay, in those cases, you can't use some of the techniques that I'll talk about later on, this gradient, stochastic gradient estimation, because you're not doing simulation. You're taking real data, and a lot of things are not available that are available if you're doing a simulation. Since you built the simulation, you know a lot about it, and you can get a lot more information out of it than if it's a physical experiment. So that's kind of the main difference. So now to outline the rest of the talk, I'll give the general problem setting, some motivating examples. Since I know I probably have a lot more slides here than I can cover, I'll spend some time on the call center, just so you get a general feel of the types of problems. I'll go quickly over the financial engineering problem, because that may be a lesser interest. Then I'll talk about these academic examples. And the reason these examples are important is because people use these to try some of their algorithms on. And you might think, oh, well, they're kind of trivial, but queuing networks are oftentimes made up of, well, multi-server queues. And a lot of complicated production inventory systems are made up of smaller inventory control systems. And one of the real world example I'll talk about here is actually uses this SS inventory control for thousands of items in their inventory. And then I'll give some differences from deterministic optimization, and then I'll go through some of the main methods, just again very quickly, like one slide for each of them except for these two types. The ones I said were the extreme points, the ranking and selection and the gradient-based works. I have a slide or two on software. There is software available here. And then I mentioned that the recent research, something I came up with, the acronyms are DIGGER and STAR for those two new methods. So this is actually a figure I had in a paper 20 years ago, and it may not be so great now, but the reason I put it up is that it kind of distinguishes between what I want to distinguish between discrete state space, continuous state space, finite versus infinite, and the fact that we'll be mostly focusing on a lot of these methods and not Markov decision processes. So now the problem setting, generally we use theta to represent the decision variables, and capital theta will be the constraint set, and we just want to minimize or maximize an objective function, so your usual optimization function. And the key is that this J of theta is estimated from stochastic simulation output. So generally it's an expectation. More recently people have been using other types of things like quantiles, conditional value at risk. There's other things, but in this talk I'll just concentrate on expected values. Okay. So these are some of the applications mentioned earlier: transportation systems, manufacturing systems, communication networks, financial systems, other service operations. So call centers I'll talk about in a second. These are just pictures. I used to have this linked to simulation so you could see pretty pictures of them, but I don't think we need to do that. Okay, so first example I'll talk about is call a contact center design. So this is done for a lot of businesses out there. Because you have to call up and you have to deal with these. So the way a lot of them do these is they have simulations of their call centers, or now they call them contact centers since they're not just voice, right? They have multiple sources of jobs that come in. They could be voice when you're calling up. It could be email. So the agents can handle calls, emails, fax. Well, fax is kind of old now, right? Not too many people fax. Now there's a lot of people, you probably used interactive web, IM chatting, you can talk with someone live. So there are multiple classes of jobs. You could be requesting an address change, something as simple, account balance, or you could be talking about more complicated problems. They overcharged you for something and it require a lot more interaction with the agent. And you probably know that, or maybe you don't know that there's a lot of these call centers actually do customer segmentation according to certain priorities. So they often tell you to enter account numbers or frequent flyer numbers or something because they say, so we can better service you, right? Actually, a lot of those times they're using this Andre, he never buys anything. He just calls up to make trouble. So we'll put him in a longer queue or something. Okay, so they have there are algorithms like that they decide right. And so obviously the stochastic elements are, arrivals. We don't know how many Andres are there versus Mike Balls, who have different types of requests. And then, of course, the agents themselves are stochastic. Some of them are better trained than others. Some of them, can do voice, email, fax, can do all of these. Some of them can only do voice because they haven't been trained. So so then the objective functions are usual things like waiting time, obviously, but percentage of blocked calls, abandonment rate, could also be the probability you have to wait more than 5 minutes. Okay, that's actually also an expectation because it's expectation of an indicator function, so that can still be used, treated in our framework. And then so there's customers that have performance measurement, and there's also the service facility, right? We could obviously make short waiting times and so forth if we had thousands and thousands of agents. They don't want to do that, right? So there's a trade-off here basically between customer service and the cost of providing service. And some of the controllable parameters of decision variables could be the types of agents, number of agents, the routing I talked about, first come, first serve versus more complicated algorithms we talked about. The call centers themselves could be networks, right? They could have some people in Hagerstown, other people in Bangalore, and where they route them, can depend on all sorts of things. So those are all decision variables that could be optimized. So this is a prototypical type simulation optimization problem people look at. Another one is options pricing. I won't spend too much time here. Basically, a call option, if people know, it's right to buy an asset at a certain strike price. And so your question is, if you have this call option, when should you exercise this right? So this is actually goes back to, it's actually a dynamic problem, so it's an optimal stopping problem. So technically, if it's actually, you can do it at continuous time, it will be an infinite dimensional problem. But one solution approach could be to parameterize the exercise boundary and then optimize with respect to the parameters, and which converts it back to a regular optimization problem. Okay, so these are the two academic samples I'll probably talk about a little bit more. So basically, this is a single server queue. It says you want to minimize the expected waiting time where you can control the mean service time. Obviously, if you just put this by itself, you would just take the mean service time down to 0 because that would make your waiting time down to 0. So we put a penalty basically inversely. You can think of this as a cost on the server speed. And this is just a one-dimensional simple problem. And you can, if it's first come, first serve, and something called an MM1Q, where it's exponentially distributed inter-arrival times of exponentially distributed service times, you can actually get analytical solution in steady state. So you could use this to kind of try your algorithms and see how well they perform versus the analytical solution. You wouldn't use this obviously in your algorithm, but you can use it to compare. Then another example that's used in literature is something called an SS inventory control. So if you have you have an item, for example, some books, or actually the one I use in my class, I say toilet paper. So you have toilet paper in your house, right? When do you go buy more toilet paper? Well, you could use an SS inventory system which says when it falls below little s, so maybe 2 rolls, then you go out, you order, you call up and say, I want some amount. I want to order up to 10 rolls. I want to have 10 rolls in the house. Okay? So obviously here there's a trade-off. If you make little s too low, you could run out of toilet paper, right? And that's not a good thing. And obviously also if you make big S too high, it costs a lot more. So there's a minimization of total cost of order holding and either backlogging or stock out cost. And again, under some conditions, you can get an analytic optimum here. So the question is, how do you solve these type of problems? Well, first of all, in both of these cases, is the domain for theta or little s and big S continuous or discrete? Right? You could just say, in the case of the first one, that I only have 5 different machines and they have different speeds at which they work, and I just want to decide which one of them is optimum based on those 5, right? Or you could have, you may say, I have sort of a machine I can control continuously, and depending on how fast I run it, it costs more according to the C. Then you have a continuous state space, right? And similarly also to little s and big S, if it's toilet paper, it's usually in units of 1, 2, 3, right? But if you, instead, if this were, say, gasoline, you know, like I think of a gas station where they fill up the tank under the ground with the gasoline. So that big S you can think of as the capacity of the gasoline tank underneath the gas station, and little s is when you go call the delivery man to fill up that thing. So in that case, you could think it's basically a continuous state space. Okay, so you have basically this question is the optimization a fixed set of discrete choices, or is it a continuous search? So I talked about the two extreme techniques that, and so that kind of says how do you model this, right? How are you going to model this optimization problem? That will tell you which type of methodology would be appropriate to this. So that's very important in the real problem, which one to use. So here is a few real-world examples. Well, I'll probably skip over the first two, one, and just go to this. Well, let me go to this one first. The Kroger. So this Edelman Award is an award in Informs, which recognizes outstanding examples of innovative operations research and analytics that improves organization and often changes people's lives. So some examples here of just to give you an idea of some of the things. So this one is a steel operation. The one that won the year before in 2013 was this Delta Commissioner of Holland, where they actually tried to protect the Netherlands against flooding. They came up with used OR techniques to do that. And one of the finalists last year was this Kroger, which was using simulation and optimization, improving pharmacy inventory management at Kroger. So that's the one I was going to show you a little bit. And the reason I put that one in there is because they use an SS inventory system, and they actually, one of the techniques they used one of the algorithms that I developed back in 1994. But so this give a short video. It's only, I think it's 2 minutes. Oh, it's not broadcasting.
Our operations group is increasingly helping us run our business better on a daily basis. Key Retail reached out to me.
I guess it can't go through these speakers.
Opportunity with inventory.
Is it connected to speaker?
It's at the, oh, okay. Doesn't broadcast through the speakers.
What's the connection for the speaker? I guess it's not there.
Oh, here, maybe.
Oh, it's right there.
Or where does that go? Oh, into the. Oh, okay,
Yeah,
all right.
Try that.
Ah, okay.
Okay. I think
All right, that
there.
should work. Whoops. All right.
At the very beginning, I was thinking of using the typical approach people have taken.
Oh, I need
But
to.
then,
Whoops.
Oh,
Sorry about that.
an analysis. But when
I was going to go to 45. Okay.
We're back then.
Okay.
Our operations group is increasingly helping us run our business better on a daily basis.
Key Retail reached out to me, and they said that they have an opportunity with inventory.
at the very beginning, I was thinking of using the typical approach people have taken. But then, actually, pharmacy has its own characteristics.
I thought we could leverage 2 stores 5 miles apart in analysis. But when you look at how doctors decide one drug over another, how the demographics might just be slightly off from one store base to another, we couldn't leverage the data from one store to the next.
It took, let's say, 1 to 2 weeks to actually understand the problem. But building a simulation model in a day and demonstrate it, 2 weeks back, people come back and they can play with the simulation model and say, hey, you got it right.
By making it unique by store, we improve the prescriptions that our customers get and reduce inventory simultaneously. We had pharmacists on the project improvement team. They could actually see the inventory pickup they could actually see the results of the different min-max when they would have been out of stock in the past.
That is a breakthrough for us.
The part of this project that hit home the most to me was the out-of-stock reduction. I have 3 kids of my own. We're off getting prescriptions late at night. And I can't imagine walking in, needing a drug or needing some prescription to take home to my child and not getting it. And so when I realized that 1.5 million prescriptions are filled every year because of Smarter Math, that really made me feel great about this project.
This project specifically, it's a win-win. Win for our customers, win for our shareholders.
Okay. So here, I'm not going to go through all of these slides. I've deleted a bunch of them as it is. But this was, at the presentation, they actually have to do another presentation as well. And so I'll go quickly through and show you how the simulation. So again, the uncertainty in here is the demand. And they built a simulation where they looked at 440 days of realized demand. And then if you look here, it says uses optimization techniques, gradient-based perturbation to find near optimal solutions. So that was the main reason I put that up. So they basically used an algorithm I developed in 1994. I didn't know about it until I went to this presentation, and the guy saw me in the audience afterwards, and he came and said, "We used your algorithm." So that's probably about the only part I'll talk too much about that. Okay. Oops. What did I just do? Okay. Okay, and then another one, which is a little bit older, was this Caterpillar supply chain management. This is actually, I think actually I'll talk about it right now since I'm here. Let's see. Oops. Okay. So this is all the way back in 2000, Fortune magazine. So it's not, oops, that's a referee report. Oh, this is getting recorded. All right, oops. So, okay, there we go. So in Fortune magazine in 2000, reported basically this work at Caterpillar, where they also were looking at how to control inventory in their supply chain. And so I think the main thing I was going to show here later on is that here it says, among the techniques that Carnegie, so this was done by Carnegie Mellon Group, used to attack this complex problem was so-called infinitesimal perturbation analysis, which I'll be calling IPA from now on. And it says here, for which no complete explanation is possible for the faint-hearted or mathematically disadvantaged. As you can see, popular press likes to put an interesting spin on it. So usually what I do is I put this up, and the rest at the beginning, and the rest of my talk is to show that that's not true, because we have smart students. I can show them in 45 minutes what this technique is about. So anyway. So that was another real world success story. So as I said, I'm talking about other people's successes, but the algorithms they used were based on work that that we looked at. Okay, so going back to kind of the methodology, what is it that makes simulation optimization hard? So, we have lots of optimizers here, so it's already hard to, regular optimization is hard, but at least an ordinary optimization can concentrate on the search. You're searching the space, whereas due to the stochastic nature of the problem, there's both search and evaluation, okay? So you think this is a good solution, but in the deterministic optimization, you're given what the objective function is at that point. Here, you're given a noisy estimate of that. So you have limited computation, right? Should you search for more solutions, or should you do a better job of evaluating the ones that you have already, right? There's a trade-off between there. So that's basically this trade-off. So this is kind of the main problem, and this trade-off is true in any stochastic optimization. It's not for just simulation optimization, but it's the trade-off between looking for better, more candidate solutions, the search, versus obtaining a better estimate of current solutions. So you can spend your computation on looking through I did have this, that's right, I was supposed to use this. through the constraint space, you know, to try to find the minimum, or estimating this theta for the candidate solutions that you have up to now. Okay, and so the key characteristic is that in simulation optimization, at least, the simulations themselves are very expensive to evaluate. Okay, so for example, a single simulation replication in some settings may take as long as to run a typical linear programming model. Okay, so we worked, Steve and I worked with semiconductor manufacturing systems companies like Intel and so forth, and so they had these very complicated simulations of their fab operations, and so if you just want them to run one day of their operations, that would actually take a lot longer than running, you know, a linear programming model. So that means you have to be very efficient in how you do your simulations, and especially if you want to do optimization. So the main approaches, again, are here. I'll go through, again, the ranking and selection in more detail. That's kind of, in some sense, the easiest to understand, because we're doing kind of the converse of optimization. Optimization, they don't have to worry about evaluation. They're just searching. Ranking and selection, there's no searching. We just have to figure out how to do the evaluation most efficiently. And then I'll also talk a little bit about gradient-based, but then I have one slide on each of the rest of these except for this one. So the robust meta-heuristics, these are algorithms that come primarily from combinatorial optimization, like genetic algorithms, taboo search, neural networks, simulated annealing. So we don't actually cover these because most of the people that do these, they handle the stochastic part in a very ad hoc way. So it's completely heuristic how they use it. So, but a lot of the software actually uses some of these algorithms. And the problem with that is a lot of times when they give you a solution, they can't tell you anything statistically about it. Okay, so ranking and selection is basically, it's a scheme of sequential sampling, and what you want to do is, if someone wants to, someone asks you, says, okay, can you give me with 95% confidence, in the same sense of statistics confidence, that you've selected the best alternative among these solutions. So the early work on this were two-stage selection procedures. Basically, you'd have one initial stage where you'd simulate all the alternatives for some fixed number of simulations, and then based on the results from that initial set, you would decide how many to simulate in the second stage, and then after the second stage, you would make a determination as to which one was the best. And the initial ones actually were the first step. The replications were used for is just to estimate basically the variance of the different alternatives. And the additional replications then would be based on this variance estimate. And the earliest ones basically were approximately proportional to the variance. So if you had alternative 1, which was very noisy, and alternative 2, which was not very noisy, then obviously in the second stage, after you found out with your initial sampling, you would put a lot more samples on alternative 1. Okay, because you wanted to get your confidence kind of much finer there. But as we'll see later, this just basing it on variance doesn't make a whole lot of sense after your initial stage. I mean, if we asked anybody out here, they would probably say, well, you should probably also look at the mean as well, not just the variance, right? Even if it's a system that, if we're trying to minimize, for example, that has very high variance, but the mean is very high as well, then you probably shouldn't put additional simulations on that one, because you're pretty confident that one's not very good still. Even though it's high variance, you don't need to know it's precise anymore. So this idea of optimal computing budget allocation basically puts a formalism to that, and it shows that how to take into consideration the mean as well as the variance. And the reason that these techniques didn't use the mean is, as we'll see in a second, is because they have to look at what they call a worst case scenario, and it's because they use a certain type of setting called the indifference zone procedure, and we'll see that in a few slides, and maybe it'll become clear at that point. Okay, so the traditional ranking and selection setting, which goes back probably 50, 60 years, is we had some set K, say K set of alternatives, and they had what they called an indifference zone setting, which is this epsilon, which basically says that if the system is within epsilon of the best, then that one's okay to select as well. So this idea of correct selection is you either select the best alternative or you select an alternative that's within epsilon and the best. So think of it as, well, I oftentimes use gold, but then you want to maximize in that sense. But okay, if we're doing gold, right, you want to find the heaviest bag of gold, right? You have 10 bags of gold sitting here on the table, right? So this indifference zone may say, okay, if it's, if we're talking about the worth, if it's within $10 of the other one, then that bag of gold is okay to be selected as well. So here what you would be doing is you would be trying to weigh each one and trying to find the one, in this case, the heaviest one, right? So the idea we'll talk about in a second of something called ordinal optimization is if you were trying to do that, what you actually are trying to do is compare the different ones. You're not actually needing to get a precise weight on each one individually and then trying to find out which one's lower. But these traditional approaches were basically trying to estimate each one precisely and then deciding which one is the best. Okay, and so one of the main approaches called ordinal optimization basically is a very intuitive notion that it's much easier to do comparison than it is to do estimation. And you can make that a little more formal, as we'll talk about in a second. So basically these procedures either give you a level of significance, so this is like your confidence, 1 minus alpha would be like your confidence level, or they'd say, I want to give you a total simulation budget, right? So if you just tell me I want 95% confidence, then ahead of time I may not know how many simulations I will require total. It could be in the billions, for example. So the other way to formulate kind of the dual is you give me the number of simulations and then I'm going to actually maximize this probability of correct selection. Okay, and your decision variables here is the number of simulation replications for each alternative. So as I said, you can do this quote-unquote optimization in two different ways. The way it was traditionally done in ranking selection is you want to minimize the total number of replications that are allocated. So this is across all alternatives, but subject to this requirement that the probability of correct selection is greater than, well, usually I think it's alpha or 1 minus alpha, depending on what this alpha is representing. So this is the traditional way it was done in statistics. And it turns out that this led to very conservative allocations. So you would be required to do a lot more simulations than needed. If you actually measured the probability of correct selection, it would be much higher. So you would get an allocation that would tell you how many simulations for each alternative, and then that would guarantee, say, 95% correct selection. But when you measured it, it would be like 99.9 instead. Yep.
In the case of your example of bags of gold,
right?
It's not more important, or more important to pick one that is not too far from being the best one in terms of weight, rather than the probability of getting exactly the best one.
Well, the problem.
It's much better to pick the second best, right?
Right.
Than to pick
if it required less amount of simulations, right? I mean, correct selection in that case would mean, so correct selection would mean if your epsilon, let's say if it was weight and your epsilon were 5 pounds, right? And the best was 1,000 pounds and all the others were 995, so they're within the inference zone. That means if you select any of them, you were correct selection. Okay, yeah.
At least as written, these look like exact dual problems.
Right, they're written, that's right. That's why I said these are like duals. But there's a little bit difference here because the way that, it's kind of fooling, right? It looks, they look like exact duals, but this probability of correct selection is defined in the traditional having this indifference zone, okay? When you actually do it this way, this probability of correct selection is something that you don't actually know, so you just assign this, and what comes out of it is the correct selection. So you don't actually know this in reality. This is the thing that's actually estimated.
It's like a p-hat.
Yeah, it's like a p-hat, right? So and the way you come up with these is you approximate this, or you come up with the way that actually is asymptotically valid.
Got it.
So, and this correct selection, however, how do you calculate this? Well, since in the real system you don't know what these are, what people have to do in order to guarantee this, they have to look at the worst case, right, where this thing is equal to alpha. Right? And the worst case is where it's just outside of the inference zone. So if it's 1,000, if this one's 1,000 pounds, then the rest of them are 995 minus a little bit, 994.9999, right? So there's only one that's best, but the others are very close to the best, right? So it's going to take a lot of simulations to distinguish that. Right? And since you don't know what your real system is, that's going to say I'm going to have to do a lot of simulations on here, whereas the actual system could be this one is only 200 pounds. Right? But because you don't know that, you have to do a lot of simulations on all of them. That's the reason why this ends up being really conservative, because they have to look at the worst case when this equality holds to derive the allocation. Whereas this thing basically says we're maximizing something that we don't know, so we don't actually know what this is. So the problem with this is you can't guarantee. It just says if you give me 1,000 simulations, I'm giving you the best allocation to maximize this, but I don't really know if this is 95% or 93%. Okay, so that might not give you enough comfort, because if it's really only 30%, then what you probably would have wanted to do was increase your number of simulations, and you wouldn't necessarily know that. Okay, so returning to this idea of estimation versus ordering, comparing versus estimation. One way I like to think about this, but they're not quite apples and apples. It's a little bit apples and orange, but it's well known that when you do estimation, the Monte Carlo convergence rate is 1 over square root of n. And so whenever I do my simulation class, I don't know if Dave does the same thing, I always tell them the precision of estimate is if you want an additional decimal place of accuracy, you have to do 100 times more effort. Okay, that's always the way I tell them. So this convergence rate is considered relatively slow, right? Because whereas if you look at this probability of incorrect selection, which you would want to go to 0. Well, what is the convergence rate of that? Well, it could also have been this 1 over square root of n, right? But it turns out this is actually an exponential convergence rate. So this probability of choosing the wrong thing goes down exponentially, whereas this estimation precision goes down just as 1 over square root of n. So that's kind of an intuitive reason why if you just want to do comparison, it's much easier to do comparisons than it is to try to actually estimate the precise value for each one of them and then doing comparisons. So that's basically this idea of comparison. So there's a lot of theory behind this called large deviations theory to kind of support this exponential convergence rate, but I won't talk about that too much. So in terms of deterministic optimization, you never have this problem because you know the exact value, so don't have to worry about that. Okay. So now I'll just give a little bit of how this works in this case. So, oops, I guess that. So here, if we look at this, these are supposed to represent 99% confidence intervals, and we're again trying to minimize. And after, say, one stage of sampling, we get these confidence intervals. So then after we do some additional simulations, we get this, and then we do more, then we get this, and then the probability now of correct selection becomes higher because probably this one can at least be eliminated, whereas here all these confidence intervals overlap. This is just roughly here. So this probability correct selection increases as you increase the number of sampling, but the question is, how do you do this efficiently? So as I mentioned earlier, these two-stage procedures that were done way back in the 70s, which were very popular until the 1990s, were based on what I call this least favorable configuration. And there, basically, higher variance meant you did more simulation. Now, here's an example I talked about earlier. Say after the first stage you got something like this. Well, you see these variances are higher, right? They have wider confidence intervals. These have low variance. Well, according to the traditional way of doing it, you would allocate more simulations to these three because they have high variance. But you can see their means are way above here, right? So logically, if you looked at this, you would say, I'm not going to simulate these more. I'm going to concentrate all my simulations on these two to try to distinguish. And so this idea of optimal computing budget allocation, formulating the optimization problem in the second way, basically leads to allocating it in that way. And I won't go through, this is basically the same thing that we wrote down earlier. But what's interesting about this is that if you formulate this optimization problem using a Bayesian model, you have to approximate this probability of correct selection. You have to, in order to solve this optimization problem, we change NIs to continuous variables, consider the asymptotic case. Then what you get basically is that the proportion that you allocate to each alternative that's not the best or not the estimated best is proportional to the variance as before, but it's also inversely proportional to its difference from the mean, okay, to the square of the difference of the mean. And then the one that's the best has a little bit more complicated relationship. So that's what I just said. So it's proportional variance and inversely proportional to squared difference in the mean. So this is very easy to implement. And so in a 3 case, basically, so the number of replications allocated to the second alternative, this should be N3 down here, increases when sigma 2 or delta 1 over 3 increases. So this is just to illustrate this, how it would work. Oops. Okay, so let me, I don't want to waste time on that. That's just pretty pictures to see. So let me just show you some actual examples. So the single server queue I described earlier, now this is actually without the cost on the server. So we want to minimize the expected waiting time. We have 10 different alternative service rates. Since there's no cost on the rate, we know the answer is the one that has the fastest rate or the smallest mean service time, since we're not penalizing it. So the answer is very simple here. So here's what the simulation, so this is something that, in your simulation class or my simulation class, you could have them do. So basically we have the proportional to variance is this purple line. Equal allocation means you just, this is what people would probably naively do. Just if you have 100 simulations and 10 alternatives, each one of them has to do 10 simulations. And if you have 200, you do each one 20. Here, though, if you use this OCBA, you can see the probability correct selection curve goes up to, higher is better, up much faster than here. So it's 3 to 4 times faster in achieving the 99% probability correct selection. And this is just with 10 alternatives. This thing actually scales better. So the more alternatives you have, the better scaling you have. So if you had only 4 alternatives, the speed up factor is less than 2. But if you have 100, you get a 20 times speed up factor by using this allocation rather than just using equal allocation. So some research in this area basically that I've worked on is correlated simulations. So all of this results earlier assume that you simulated all the alternatives independently. Okay, in simulation, people do what's known as common random numbers. They try to use this, stochastically similar situations for each of the different alternatives, because that'll induce positive correlation, which will increase the probability you'll be able to tell which one's better. It's like if you're doing 2 alternatives and you give them similar situations, then you probably have a better idea of the relative performance of the 2 than rather than if you just gave them 2 independent randomness. Then maybe other things are, if you want to, instead of just selecting the best, you might want to select a subset. You can say, so if you have 1,000 alternatives, you may just say, can you give me the top 10? Because I may not just want the number 1. Then also fully sequential procedures. So those procedures that we talked about earlier were based on asymptotics, and they were done in 2 stages. The first stage is to estimate the parameters that were given in the asymptotics, and then the second stage is to allocate the remaining budget according to the asymptotic result. So we've been looking at fully sequential procedures, which would mean you allocate one simulation replication at a time. You know, which one should you simulate next among all the K alternatives? And the last thing actually that we looked at is actually anti-intuitively, the probability of correct selection may actually decrease as the number of simulations is increased. You know, you would think intuitively as you do more simulations, your probability of correct selection should increase, right? Because you're getting better estimates. Well, it turns out that there are counterexamples, and they're little odd cases, but they're not completely, you know, wacky, where if you don't do your allocation right, then you can actually decrease your probability of correct selection. Okay, and intuitively, it's the case where if you know the best one pretty accurately, so the variance is already small, if you continue to simulate that one, you're actually wasting your time. You should simulate the ones around it that are, you know, where you don't know as precisely. And it turns out that if you can show that in certain scenarios that if you keep simulating the one that's actually the best and it has already very low variance, your probability correct selection can actually go up. I mean, go down instead of up. Okay, so I'll talk briefly, since I'm running out of time, on gradient estimation and the techniques. So this is the area I work mostly in. It's techniques are perturbation analysis, especially that infinitesimal perturbation analysis, or IPA, where we read in the Fortune magazine that the faint-hearted can't understand. But it's actually quite simple. And then there are other techniques called the likelihood ratio, score function method, weak derivatives, simultaneous perturbation. So I won't go through the technical details of it. Actually, I was going to give a personal aside here on connecting research and teaching, just maybe for the students. Something what my advisor used to call a virtuous circle or cycle, or it's, you know, good positive feedback relationship between research and teaching. This direction is pretty obvious. You know, you do research and then you teach, you know, PhD students. You bring it into your classroom. You teach them about all the great results that you or your colleagues have come up naturally. But I've found out that this part, you know, which my advisor also told me, said that just by teaching the students, sometimes you come up with very interesting ideas in the research too. So, you know, you teach, there's textbooks that have been written for 20 years and they do the same thing the same way all the time, and you start teaching it, and then you think about it and say, well, maybe you can do things a little better. So this SS inventory control was one example that I did in my paper in 1994. I was teaching this to MBA students, and I'd never actually done this class before myself because I didn't come from a business school. So, you know, now they would never allow me into the classroom. You know, they don't allow people into the MBA classroom with no experience in that course. But at that time I did. So I was teaching them SS inventory control, and I was thinking, well, you know, if you had, you know, complicated systems, you might have to simulate this. Can I apply this IPA or this other versions of PA to that? And that actually turned out to be a paper I wrote back in 1994, which led to some of these other applications that I talked about. And another one was actually this financial derivatives textbook, which I'll show in the next page, where what drives research besides money? So intellectual challenges. So in a very old paper, basically this guy Boyle, who introduced Monte Carlo simulation to the finance community, and this is like one of the most cited papers in finance, even though it's such a simple idea. He just told finance people, okay, you can use Monte Carlo simulation. Okay, and so, you know, they started using it, and on Wall Street they use it all the time. But he said that basically to obtain option values corresponding to different stock prices, each set of simulation has to be carried out for each stock price. And then these are two textbooks that are used, financial derivatives. They made statements like Monte Carlo simulation can only be used for European style options. This procedure is essentially only useful for European-style options. So these are cases where we motivated us to come up with algorithms that prove that these weren't true. So if you look at subsequent editions of this whole book, it no longer has this statement anymore. So that's what these are just kind of an aside, what drives research besides money. Okay, so actually, I guess I'm out of time. So the stochastic approximation basically is a gradient-based technique in the stochastic setting. And this big pi here is just a projection onto the feasible region. And this is a gradient search. And the main thing is how do you determine the step size and how do you estimate the gradients. And so these techniques I talked about, direct estimators, perturbation analysis, likelihood ratio, and weak derivatives, estimate this with unbiased estimator. Indirect estimators are these other ones. And this was just a table to kind of show you, but I don't have time to cover that. That's one I talked about earlier. So just to give you an illustration how this works, when you're doing simulation, traditional, if you're trying to estimate a gradient or just a derivative, you would simulate at theta, get an estimate of that output J of theta. I guess I called it L of theta omega before. Then you change the parameter value, do another simulation, take the difference and divide. So that's what people did for many, many years, right? And if this weren't a simulator, this were real data where you were out there in physical system, then this is probably the only thing you can do. But it turns out that in many systems, we know enough about the simulator that if you put in an intelligent algorithm, then you can get a direct estimate of this gradient without having to do resimulation. So for the single server queue, for the SS inventory system, there are techniques that allow you to do that efficiently without having to do this resimulation. So in that case of the pharmacy drug, if they had, they said they had thousands of different products where they'd have to determine these little s and big S, that's a huge savings. Then if you would have to simulate, for every little s and big S, that'd be a lot of simulations, whereas they're able to find it with the same simulation and do it a lot more efficiently. I think it's already past 5, so I'll probably skip this. Yeah, I'm going to actually skip this. Okay, so let me just talk a little bit about simulation optimization practice. Now, if you go to any discrete event simulation software package, so like next week, the conference I go to, Winter Simulation Conference, there's always a lot of software vendors there. So back in 1990, when I first started going to this conference, none of these packages had a quote-unquote optimization algorithm in them. Now, almost every one of these has to have it, otherwise they feel like they're behind the other vendor. And as we saw, the spreadsheet packages now even include a simulation optimization. All of these discrete event simulation textbooks now have a new section on this topic as well. So some of the software just that is out there, OptQuest, AutoStat, which is part of this package that dominates the semiconductor industry, SimRunner, and then in RiskSolver, now there's actually also a simulation optimization package. So these are some of the simulation software that's out there, and they all now have optimization routines as well. Okay, so I guess I'm out of time, but I'll spend a few minutes just at least defining these acronyms because it took as much time to come up with this. So both of these are recent research with 2 PhD students, one who graduated already is at Google and another who's going to graduate next year. And these ideas basically were enabled by the simulation setting. So it's very different than normal stochastic optimization. And the main idea is very simple. We talked about how if you're doing, say, gradient estimation or gradient search in deterministic optimization, you would just use the gradient. There's no reason now to use the actual objective function value because you know the gradient exactly. But in simulation setting or stochastic setting, if you know both, if you have estimates of both the objective function or performance and the gradient estimate, why don't you use both of them? Okay? Traditionally, what would happen is people would either just use this because they didn't have a gradient estimate, what I call the direct gradient estimate, or if they did have a direct gradient estimate, they would just use that gradient estimate to do their search, just like in deterministic optimization. Here we're saying, since these are stochastic, you shouldn't throw away this information. You should use them all together. And so these algorithms basically use these together in an efficient way. And so I was, if I had time, which I didn't, I was going to go through the PDF that basically looked at this in the regression setting. So it's something called direct gradient augmented regression. Everybody's used regression before. So you have output points, you fit, a curve, let's say a line. What happens if you also have, derivative estimates there, right? If it's a line, you can obviously get a better estimate. Everything's noisy. The output values are noisy and the gradients are noisy. But now if you use both of them, you can do better than if you just use, just the performance measures themselves. And so this work basically studied under what conditions you would do better. Because if, for example, if the gradients are extremely noisy, you have to do weighting of how you do this. So actually, maybe I can quickly go. Thought I had it here. Oops. Oh, no, I don't seem to have lost it. Okay. Well, so basically, when you did your basic regression, the first way I think they taught you was probably using least squares, right? You did least squares, you did calculus, and you came up with your estimators for the betas in regression. Well, now that if you have the gradients or the derivatives as well, basically you can formulate another least squares problem. But the question is, when you do this least squares, how do you weight each of the two estimates differently? And so basically we studied how you do this weighting relative, and it turns out it's obviously, I mean not obvious, it's intuitive. The solution comes out that this weighting of the two parts is going to be proportional to variance, right? So if the output measures are very noisy and the gradient estimate is relatively less noisy, then you should, so inversely proportional actually, you should weight the one that's more accurate, basically, more. And so then we wanted to apply this in response surface methodology, which I didn't have time to cover. The other one was this, what we call STAR, which is called secant tangents averaged stochastic transformation. So STAR is the secant tangents average, and again, how that works. Oops. I have one last figure here. It's a very simple idea. It's the secant line is this line that goes between the 2 points. So if you were only going to do finite differences, this is what you would use. Traditionally, whatever point you were at, say theta n, which is in between, you would just, if you have a direct gradient, you would just use that tangent. But this is saying, now, okay, let's not do that. Let's look at these 2 points, and if we have direct gradients, let's use the tangents there, average that, and then again we take a convex combination of these two gradients and see how that works in gradient search. And of course, under certain conditions on the noise and on the weighting, you can do better using this. So I think that's the last thing. And these are just some references for them. So I think with that, I'll go ahead and stop and take any questions. Any questions?
A few questions.
Yep.
With the secant tangent search, for each point, are you running three optimizations? Because it looked like you had like a plus epsilon and a minus epsilon.
You're running two simulations, yeah. You run one simulation here and one simulation there. But you would have a theta, which is the, theta n is the midpoint of this. So you wouldn't actually simulate at that theta. You wouldn't have to simulate at that point. You just say that maybe my best estimate right now is whatever, 3.2. So I'll simulate at 3.1 and 3.3, get the estimates there and the gradient estimates, use that to decide where I go next.
You're assuming those two gradient estimates are equally good, so you're just taking the average of those two, but then you have to weight how you combine those with.
That's true. Yeah, actually, these two could also be weighted as well. Right. That's a good point. Yeah.
Touching about the point that you mentioned about teaching, going toward research, which I think it's, to me, that's also very exciting. Have you ever had the experience of combining applications in your teaching and introducing the students directly to applications and working out the problem collaboratively with colleagues from other disciplines?
From other actually, I probably haven't done that. I mean, I guess the closest we've done to that is we used to have these things in the business called group field projects, but I wouldn't call that research, though. That was more like consulting. Basically, we would go out there and solve the problems they had out there in the business. For example, there was one case where we worked with Pepco to, again, determine inventory levels as well. But that's probably the closest that I got to that.
That would be interesting.
Well, I mean, yeah, that's probably the closest, because usually what we do is, if we work with industry, we have our PhD students go out there and work in the internship. So, for example, at Intel or AMD, they actually just go out there.
I see a lot of case studies, for instance, only in my field alone, that could benefit significantly from some of this.
Yeah, I mean, I think that's a good idea. Yeah.
Yeah. I guess this is just a general question for simulation optimization, but at least to me, it seems like all thetas are not created equal. That is, running a simulation with some parameters is way harder than with others.
That's true. I mean, more expensive, you mean,
yeah.
Right. Yeah, so, I mean, I guess in one of the examples, the ranking and selection, since that's in some sense the simplest, so yeah, I guess that formulation basically you were looking at. Oh, here. Right, so here as you said, basically it's summing NI, right? Or here's summing NI. So instead of just counting number of replications, you could put CINI. So that's one of the extensions that we've looked at. I mean, that's because depending on where you are or which one you're simulating, it will cost a different amount. The question is whether you would know that ahead of time. So in this formulation, you may not know it ahead of time. So here we would assume you knew it, but in other cases, you might not. Right.
It's sort of an extension of this idea of importance sampling, where your importance is derived not just from the variance of the underlying estimate, but some other fact that you might know about that particular set of parameters.
Yeah, that's right.
There's plenty of things you can simulate where if you're over on this end, the computer has to do a hell of a lot more work.
That's right.
There's going to just be a lot more entities running around in
That's right.
circles. Whereas if there's almost nothing going on, so you're over at this end of the space, then,
Yeah, so exactly.
Variables are done.
Right, exactly that queuing system, right? With the
queuing systems are exactly
because sort of you have a monotonic, it behaves monotonically, so you would have the idea there. Yeah.
I have a general question. So our groups works in the field of semiconductors, integrated circuit, and do you have any examples that you can apply those stochastic optimization to the semiconductor integrated circuit research?
Well, you're looking at the actual process level, right? Not the operations level.
No.
Yeah. So we've worked with the operations level, right? We have not looked at the process level so much. I think most of the stuff that's done there is deterministic combinatorial optimization, right? Because Mike, I know, has done a lot of stuff in that area. But we haven't looked at that level.
Thank you.
Because, I mean, I guess in some sense we're not sure which part dominates, right? You may argue that the stochastic parts there are not the dominant factor. There are other things that may dominate.
Well, as the technology now shrinks, many are arguing that the variations in the devices are becoming a dominant factor.
Oh, okay.
So,
all right. Well, it's not really determined. Okay. Well, then it's a potential area that could be applied. Okay.
I think, that's exactly what I was trying to.
Okay.
Let's thank our speaker again.